Today, I would like to discuss the mechanical property of the orthopedic implant material and their specific application. I have no conflict of interest to disclose. First, I will present our case. The patient is a 53-year-old man who presented with malunion index finger fracture with rotation deformity. We performed corrective osteotomy using the plate. Unfortunately, during the follow-up period, the plate failed due to the mechanical breakage. The case ultimately required revision fixation with a higher strength plate. As illustrated by this case, predicting the mechanical durability of the plate under postoperative condition remains a significant challenge in our practice. This leads us to consider the determinate factor of implant mechanical properties. Every implant requires adequate stiffness and strength. Stiffness determining the resistance to deformation and strength determining resistance to failure. These mechanical properties are regulated by the two fundamental aspects: the implant's geometric configuration, specifically its structural characteristic, and the metallic material's metallic properties. Consequently, the selection and understanding of metallic materials are fundamental to using the interfixation device. Various materials are used in orthopedic implant, including titanium, stainless steel, and cobalt chrome alloy. These medical implants are regulated by ISO international standards with regulatory specification regarding the mechanical strengths. Let's begin by examining their key characteristics. Let me begin with titanium, which is the most commonly used material in fracture implants. Titanium can be characteristic into pure titanium and titanium alloy. Pure titanium refers to titanium with a purity of 99.4% or higher, with a density of 4.5. Titanium is relatively lightweight. In terms of strength, depend on its grade. Both its yield stress and tensile strength are comparatively low. It has Young's modulus of 105 gigapascal, making it relatively soft and exhibit high ductility. Furthermore, one of the most notable characteristics is excellent biocompatibility. To address these limitations, titanium 6 aluminum 4 vanadium alloy was developed by adding aluminum and vanadium to pure titanium. This alloy maintained titanium's excellent biocompatibility and favorable softness while achieving significant improved strength. However, it exhibits lower ductility and is more resistant to plastic deformity compared to pure titanium. And potentially concern has been arised regarding the possibility of vanadium leaching from the alloy, which may have implications for human health. In recent years, titanium 6 aluminum 7 niob alloy, where vanadium has been replaced with niob, has become to use in medical applications. More recently, new titanium alloy that offer even greater combination of softness and strength have been developed and are being considering for implant application. On the other hand, stainless steel, which is commonly used in the past, is characterized by its hardness. It has a high density of 9.7, making it nearly twice as heavy as titanium. Additionally, it exhibits high ductility and is easy subject to plastic deformity. However, one significant drawback is its relatively post-biocompatibility. Cobalt-chrome alloys were characteristic by their high Young's modulus, making them both hard and strong materials. These alloys also demonstrated excellent biocompatibility. Furthermore, they exhibit superior wear resistance. Due to this outstandard wear resistance, cobalt-chrome alloys were specifically utilized for the articular surface of artificial joint. So, how should we think about the hardness of these materials? When considering the optimal rigidity for fracture fixation that promote bone healing, the key factor is the strain generation in the cast tissue at the fracture site. The relationship between the bone formation and strain is well known as parent strain theory. When strain is below 2%, bone healing occurred without cast formation. This is as known as primary healing and is achieved through the interfixation. This provides absolute stability. When strain is controlled between the 2% and 10%, bone healing occurs with favorable cast formation. This is termed secondary healing, and this type of fixation is referred to as relative stability. Finally, when strain exceeded 10%, as instability state occurs where the formed cast is destroyed, leading to hypertrophic non-union. So, what are the factors that determine the strain in the cast tissue? There were the width of the fracture gap, the rigidity of the implant, and various external forces. The width of the cast is influenced by both fracture pattern and the reduction method, while external forces are determined by body weight, lifestyle, and rehabilitation protocol. Then, what determines the rigidity of the implant? It depends on both the material property and geometry, specifically the type of materials used and its cross-sectional area. However, measuring these factors in clinical practice is extremely challenging. One approach is to measure is through finite element analysis. We created a simple fracture model with either non-gap or 1 mm fracture gap. The fracture was fixed with a 7-hole locking plate using 3 screws on each side of the fracture. The plates were modeled with material property of pure titanium, titanium alloy, and stainless steel. We created a cantilever bending while the distal end is constrained and posterior load of the 100 Newton was applied. In the fracture contact model, we observed no significant difference in mechanical behavior between the pure titanium, titanium alloy, and stainless steel plate. when the force is transmitted through the plate to the opposite side of the fracture in case where there is adequate fracture site contact. The load distribution between the plate and bone remains similar regardless of the implant material. In other words, the result demonstrates that stable fixation can be achieved with any of these implant material when there is direct bone contact. In contrast, the model with a 1 mm gap clearly demonstrated the direct influence of the plate material property. Let's first examine the equivalent stress on the plates. Comparing titanium, titanium alloy, and stainless steel, pure titanium plates show a complete failure through the breakage. The titanium alloy plate, due to the higher yield stress and tensile strength, did not fail. Stainless steel plates exhibit only plastic deformity. When the focus on the strain between the bone fragments, we observed that implants made of the stainless steel maintain the lower minimum principal strain at the fracture site. Let's quantify these observations. Pure titanium plate fell at around 40 Newton of load, after which the strain at the fracture site increased significantly. The titanium alloy shown in blue did not fail, and the strain continues to increase until the bone fragment made contact. In contrast, stainless steel, with its Young's modulus being twice that of the titanium, demonstrates its rigidity by limiting the strain to approximately half. While this outcome might be obvious given the difference in Young's modulus, it clearly demonstrates that stainless steel is more effective at the control strain. What happens if we reduce the plate thickness by 1 mm? We model and compare the three scenarios. The original titanium alloy plate, a titanium alloy plate reduced by 1 mm in thickness, and stainless steel plate with the same reduced thickness. Analysis shows that the thinner titanium alloy plate with its reduced rigidity result in greater strain at the fracture site, with bone fragment make contact at approximately 20 Newton. However, the thinner stainless steel plate, due to its high Young's modulus, maintain rigidity comparable to the original titanium alloy plate and demonstrate nearly identical mechanical behavior. These findings suggest that if we want the thinner plate, stainless steel might be the more suitable material selection. The plate we used in our previous analysis was based on the variable angle locking hand system by Debussy, which is manufactured from pure titanium. On the other hand, this implant system is also available in stainless steel. From mechanical perspective, the stainless steel version offers both high strength and rigidity, making it potentially more advantageous for finger implant. However, mechanical properties are not only the consideration. Biocompatibility also plays the clearest role in plant selection. What is biocompatibility? Biocompatibility can be defined as a degree of local tissue response or systemic reaction caused by the foreign material in the body. This phenomenon is due to the surface topography of the material. Let's compare the surface topography of the stainless steel and pure titanium. Stainless steel, after electrical polish, exhibit the extremely smooth surface texture. Under electron microscopy observation, the stainless steel surface shows the average roughness of the approximately 0.1 micrometer, indicates a very smooth finish. In contrast, titanium displays a much rougher surface texture with an average roughness of nearly 1 micrometer. Due to this rough surface topography, titanium achieves direct osteointegration with bone. Therefore, it is particularly suitable for implant intended for long-term or permanent placement. In contrast, smooth surface of stainless steel does not facilitate fibrin stabilization and prevent bone on growth. However, it does promote fibroblast proliferation and encourage soft tissue encapsulation. Consequently, it is more suitable for implant that is tend to be removed. Let's examine in detail the interface between the plate and soft tissue. The smooth surface of stainless steel promotes cups formation while minimalize adhesion. In contrast, titanium rough surface tend to from direct adhesion with soft tissue. In hand surgery, where tendon adhesion are significant concern, this characteristic given stainless steel a distinct advantage. In conclusion, stainless steel implant with a lower biocompatibility and a reduced tendency for the tissue adhesion proved to the superior for hand application from the both mechanical and biocompatibility. As a take-home message, we have reviewed the fundamental concepts essential for understanding metallic implant materials, including stress, strain, construction property, and material characteristics. Based on these concepts, titanium provides excellent biocompatibility, and through alloying, we can achieve increased strength. Stainless steel, on the other hand, exhibits minimal tissue adhesion and high rigidity, making it particularly suitable for upper extremity implant where thinner is required due to the tendon proximity. Therefore, the selection of metallic material should be based on the specific implant location.